Whether you've wanted to or not, chances are you've probably heard about AI by now, and all of its amazing benefits. How it's going to enslave all of humanity, take all of our jobs, and keep us around as little meat pets that it can torture at for fun. Now, while this is all well and good, if you're like me and you use a slightly older computer, you're probably struggling a little bit to get on the AI wave. I mean, how am I supposed to ask ChatGPT a question if I can't even connect to the internet? Well, luckily for all of us on slightly older machines, I've written a little program that'll help us get a little taste of this AI mumbo jumbo. Alright, this isn't exactly ChatGPT or anything, but it is a neural network, so I think it counts as an AI. And it's running on a really old and very slow machine, which I think makes it interesting. Alright, before I yap for an hour, let me just give you a quick demo. Here there's a little canvas that you could draw in with a mouse, so I'm going to draw a little digit here. I drew the number 2, and if I press enter, you can see, hey, my neural network correctly guessed that I drew the number 2. Awesome. Let's give us a couple more goes just to make sure that wasn't a mistake. Let's try a couple other numbers. 8's a pretty good one. Correctly guessed that's an 8. Let's try the number 9. Now I actually know the number 9 is actually a bit of a weak spot for the model. Oh, but it got it there. Let's try a 1. It's a funny looking 1, but still got it. And then to finish it off, let's go with 6. Good old number 6, and you got that too. Nice. Now, it's not all sunshines and rainbows. You can trick this model into giving the wrong answer, and a really dependable way of doing that is by drawing the digit very small and to the corner. So if we draw a small number 2 here, try asking it what it thinks that is. Yeah, it says it's a 7. That's obviously very wrong. And if we try a small number 8, yeah, it doesn't get that right either. Let's try like a small number 1. Oh, well, it actually got that right. But if you look at the ranked predictions here, it's equally confident that this is a 1 and that this is also a 4. So it's clearly not very accurate in this situation. Now, one thing I'm sure you have noticed is that this model seems to run fairly quick. It's a pretty short delay between me asking for an inference and then it giving me one. And this might be a little surprising to you, especially if you're familiar with the original Macintosh, because, as you might know, this is a very old and a very slow computer, and generally running a neural network is associated with requiring a lot of computing power, which is because it does, generally. So I think we're going to take a second and stop the demo, and I'm going to yap for a bit and explain how exactly I've managed to get a neural network running fairly performantly on this very, very old hardware. And before we can do that, we need to talk about 2 things. 1, how does a neural network even work? And 2, what's actually inside the original Macintosh powering it? At its simplest, a neural network is just a function. Like any function, it has inputs and outputs. In our case, the inputs will be the 28 by 28 pixel image that we want to inference, while the output will be a list of 10 probabilities matching to the 10 digits that the input image could be. We're going to represent the inputs and outputs here as nodes. In between the input and output node layers, we're going to have an extra set of nodes that we're going to refer to as the hidden layer. To see how connections are made between these layers of nodes, let's look at a single node in the hidden layer and see how it makes connections. All this node does is it takes the values from the previous layer's nodes, multiplies each one by a different weight, and then sums them all up. Or in other words, it takes a weighted sum of all of the previous input nodes. There's one final bias value that gets added to all this, and then all of this is passed through what's called an activation function, which I won't talk about right now since it's not actually that important. But that's basically it. Since we're taking a weighted sum, the weights that we're going to be using will have a decimal component to them. The way we usually deal with decimal components on a computer is by using what are called floating point numbers. It's worth noting that the inputs, outputs, and bias values will also have decimal components to them, so we end up representing everything in the model with these floating point numbers. To summarize, in order to do inference with a neural network on a computer, we need to do floating point multiplications and additions, and do them fast. So let's take a look at the Macintosh hardware itself and see what it gives us in order to accomplish this. Here I've got my Franken Mac. This is my Mac 512K that I leave open. Now, there's a specific reason I leave it open like this. I'll talk about it later in the video, but for now, let's use this opportunity to take a quick peek inside the machine and see what's powering it. Now, there's two main parts of relevance for us today, the CPU and the memory. As the name suggests, my Macintosh 512K has 512 kilobytes of memory, which you can see here. Now, this is already a pretty anemic amount of RAM, but it actually gets worse. This is because I decided to target all of the original Macintosh line, including the very first Mac model, the Mac 128K. And if the name didn't give it away, that only has 128 kilobytes of RAM, a truly pathetic machine. And this is our first big limitation when it comes to running a neural network on the Mac, getting everything to fit in RAM. Moving over to this big chip in the middle of the board is the main processor, the Motorola 68000. Released in 1979, it's a truly ancient part, and it's clocked at about 7.8 megahertz in the original Macintosh, although for some reasons I'm not going to get into, it's more equivalent to a 5 to 6 megahertz part in the Mac itself. Despite its age, it actually has a couple of surprisingly modern features. For example, it has a full 32-bit register width, which, well, I guess it's kind of modern if you're from the late 90s, but still, pretty impressive for a chip this old. Now, one thing it doesn't have, though, is something called an FPU. To explain what an FPU is, we need to go back to talking about numbers. I mentioned floating point numbers and how you can use them to do decimal arithmetic on a computer, but if you just need to deal with non-decimal numbers or integers, you can do that too. You can directly represent integers on a computer. In order to do math with these numbers, there's a part of the processor called the ALU, or the Arithmetic and Logic Unit, which, as the name kind of gives away, does arithmetic and logic operations on integer values. Floating point numbers, being a completely different way to represent numbers at all, requires a completely different part of the processor in order to do math with them, and this part is called the FPU, or the floating point unit. Alright, enough beating around the bush. To get to the point, the original Macintosh cannot do floating point math directly. The Motorola 68000 has no FPU, and so it doesn't have the capability to do this floating point math. This, as you can imagine, is our second big limitation. As I've just told you in the last section, we need to do a bunch of floating point multiplications and additions, and we don't have a floating point unit. Alright, now that we've covered all of that, let's get to actually running a model on the Mac. And before we get to my final solution, aka what I've done for the demo earlier, let's talk about a naive solution first. A solution I like to call just doing it. Now, what do I mean by just doing it? Well, let's look at our two limitations again. Our first limitation is the amount of memory we have. We need to have the model fit entirely within a really small amount of RAM. Now, before we get clever about doing this, why not just take the obvious approach of just making the model smaller? If you only have 32 nodes in your hidden layer, you'll have a lot fewer parameters you have to store in memory. And yeah, your model accuracy will be worse, but you could just do it. Looking at our second issue of not being able to do floating point math directly, there's no reason we can't indirectly do it. In fact, this is a pretty common thing. It's called floating point emulation. It lets you do floating point math using an integer ALU. It's obviously not going to be anywhere near as fast as a floating point unit, but you can just do it. Now, I actually forgot to save my code for this, and part of the reason was the results were so underwhelming I saw no real reason to keep it around. But if you do both of these things, you can very slowly, as in almost 10 seconds to inference slow, and very inaccurately predict a number from an image running on the original Macintosh. Now, this is very obviously not what I showed at the beginning of the video, so let's cut to the chase and get to the actual solution, a technique known as model quantization. Now, while what I'm doing here might seem a little bit silly, trying to get a neural network to run on a machine that could barely fit it, it's actually something that comes up a lot today. With large language models being all the rage, there's a huge demand to run it on consumer hardware. But even with our modern computing technology, consumer hardware is still barely enough to run some of these models. So there's been a lot of techniques developed in order to get these models to fit and to run on this hardware that's, well, a little too weak to run the full fat deal. One of these techniques, as I've just mentioned, is model quantization, and it's what I'm doing here to run this model at anywhere near the speed and complexity that I want. To explain the idea, let's go back to our neural network for a second. Specifically, let's look at the weights for the hidden layer. Here I've got a little plot going, and this plot right now is scaled to show you the entire range of a 32-bit floating point number, which is about 2 to the power of 127, so it's a pretty big number. Now, you might notice these vertical lines here, and this is actually because this is a histogram. I'm plotting the specific values that occur in the weights for that hidden layer. The very clear thing here is that we're using almost none of the range of a floating point value storing these weights. They occupy an absolutely tiny sliver of the range that a floating point value can truly represent. Naturally, then, you might wonder if we can store these weights in a smaller representation with less range. For example, an 8-bit integer. We can't do this mapping naively, though. As an 8-bit integer only stores integers between negative 128 and positive 127, a simple remapping would cause us to only use around 4 or 5 of the 256 unique values that an 8-bit integer could represent. Instead, we can have an implicit scaling factor that we have alongside the integer. This scaling factor would effectively let us compress or expand the integer range to better match the range of the numbers that we want to represent. Now, this gets us pretty far, but if you look at our values closely, you'll notice that we have more negative weights than we have positive weights. To compensate for this asymmetry, we can add one more value, an offset value, that'll let us shift the entire range to the left or to the right to better fit these asymmetric cases. And that's basically it. That's model quantization. Since an 8-bit integer only takes up 1/4 the amount of memory compared to a 32-bit float, we can effectively store an entire layer's worth of weights in 1/4 the amount of memory that it took before. Remember that this scale and offset is shared for all of the weights in a layer, so it adds a very negligible amount of storage on top of what we already have to store. This effectively solves the first problem we have, fitting the model into RAM, and we get to do this without sacrificing any model complexity from removing nodes or anything like that. There is a slight hit to model accuracy with model quantization, but it's nothing compared to making the model significantly simpler as we had done before. Now we're just left with the issue of doing floating point math quickly. After all, after we add back the offset and multiply the scaling factor, we're effectively left with a floating point number again. Or at least, that's what it seems like at first. Instead of converting back to floating point numbers for the calculations, what if we just did our multiplications and additions on the quantized values themselves? Now at first, this might not make a lot of sense. After all, as I've just mentioned before, each one of the model layers have a completely different scale and offset to them. So it seemingly doesn't make sense to just do multiplications between them. But if you think about it for a second, the result of this multiplication would actually be the product between the input and the weight divided by the product between the two layers' scales. We could sum up all of these values without issue, since they all have the same scale, aka 1 over the previous layer's scale times the current layer's scale, and then all we have to do at the very end is convert them to the output layer's scale. And doing this is pretty simple too. It's just the previous layer's scale times the current layer's scale divided by the next layer's scale. And just like that, we can get rid of almost all of the floating point math that we were doing before with nice and fast integer math. And thus, model quantization also solves the second issue for us. Alright, I'm simplifying a little bit. While model quantization was definitely the big optimization that helped bring this into the realm of possibility to begin with, there's 2 other important optimizations I've employed that I think we should also talk about, and also were really instrumental in getting any of this working in the first place. Now, I explained earlier that I would explain why my Macintosh was half taken apart like this, and if you've watched my last video, you already know the reason why. But basically, I've been doing a lot of reverse engineering of the original Macintosh line, and this is because I've been writing an SDK, or a software development kit, that lets me write applications that run bare metal directly on the Macintosh hardware, completely bypassing the original operating system of the computer. As I mentioned, this SDK is still under development, so I haven't released it yet. I hope to release it soon, whenever that is, aka whenever I find free time. But in the meantime, I have been testing it, writing these little applications like this and my previous application, which was a Chip 8 emulator. Going bare metal means that I've had to basically rewrite everything from scratch when it comes to hardware interaction, including writing my own custom bootloader. In fact, I think this might be the only bootloader that exists on the Macintosh other than Apple's official bootloader for loading macOS. Now, I'm not just shilling my Vaporware SDK that I haven't released yet for no reason. It is actually relevant to running a neural network. The main thing being that going bare metal, it lets me claw back memory that would normally be taken up by the operating system. Even at idle doing nothing, macOS, or as they called it at the time, system software, uses about 20 kilobytes of RAM. And on a Macintosh 128K, that's about 20% of your working system memory when you take into account that your frame buffer also takes up another 22 kilobytes. As I've talked about plenty enough in this video before, memory is a huge issue for us trying to get the neural network to actually fit on the machine. So obviously getting back this memory is a huge savings for us. The final optimization was actually completely unplanned for. You see, the interactive part of this demo was actually the final part I wrote. I originally started with the actual neural network inference code itself, and in order to test the neural network, I would basically statically include a test image from the data set I was using and just run that through the model and saw if it gave me the right result. By the way, the data set that I used for this project was the MNIST handwritten digit data set, and this is kind of like a canonical baby's first data set to use when training a neural network. And this is also where the name of the program comes from, the MNIST in MacNIST 68000. Anyway, I saw the neural network was successfully inferencing these little test images that I was taking directly from the dataset. So I was like, cool, let me actually write the interactive part of all of this. And I did that, and then I decided to try it out. I wrote a little digit, I pressed enter, and well, I mean, here it's giving the right result, but at the time it was giving me complete garbage. The inference was just wrong most of the time. To cut a long story short, basically a random doodle that you're going to make on a little canvas is actually not going to look a lot like the actual MNIST dataset digits themselves. There's a lot of processing done to the digits in the dataset. This is just to normalize them and I guess to just make it a easier thing to train a model on. But obviously that all wasn't going to help me here because I wanted to write this interactive demo where you draw a digit. Anyway, the solution to all of this was either to write a bunch of image processing code that ran on the Mac, which I kind of didn't want to do since that would slow everything down, or to just retrain the model on data that looks more like actual handwritten digits. Now, I wasn't about to make my own handwritten data set because I don't got time for that. So instead, I used a technique called data augmentation, where I took the existing MNIST digits and then I applied various transforms to that, mainly applying random scaling and translations to the images, and then training the model based on these. The thinking being that applying these random scales and translations would more closely approximate a randomly drawn doodle. Anyway, as you can clearly see through all of the demo giving that I've done today, that clearly worked out. This is basically the final step to getting the model to actually run for this demo. And yeah, that's basically everything. I apologize if the video was a bit much at times, but forgive me, there's only so much you can do when you have to explain how quantized neural networks work in just a couple of minutes. Now, I'm going to be releasing two things today. The first thing is the actual disk image for this, so you can try running this on either an original Macintosh, I'll have the compatible models up here, or in an emulator. And by the way, I have some really good news on that front too. I mentioned in the last video that there was only one emulator that existed that was accurate enough to emulate such bare metal software, but the developer of Snow actually reached out after the last video. He asked for a couple of code samples, and so I sent those over along with some logic analyzer captures, and well, I'm really happy to announce that Snow also can run all of my SDK software without much problem. You have to enable one setting. I'll put that up on the screen here in order to get the mouse to work properly. But yeah, I'm really happy to announce this because MAME's pretty annoying to set up, so having a much easier to use emulator like Snow to run this software is definitely going to be very nice. The second thing I'm going to be releasing is the neural network code itself from this project. I'm not releasing the full application code for the actual Macintosh part of this itself because, well, the SDK isn't out, so you wouldn't be able to build it. But I think the neural network code is definitely going to be a helpful reference if you want to implement something like this yourself, especially the quantized inference code. I actually couldn't find an example of it already existing on the internet, so hopefully this will save somebody some trouble. And in that repo will be all of the training code and the code for making the augmented data and all of that stuff that I mentioned today. And I've tried setting it up in such a way that it should be fairly easy to port to other, let's just say, silly platforms. One final thing I want to mention is that this being bare metal software, there's a lot of weird quirks in actually getting this to run. So please read the README included with the disk images very, very carefully. I'd hate for somebody to run into a bug that could otherwise be avoided. Anyway, I hope you learned something today, or maybe even found this a little bit interesting. If you like this sort of technical tomfoolery, please consider subscribing. Unfortunately for everybody, I'll still probably be doing stuff like this in the future. And with that, leave a like, comment, all of that sort of stuff everyone already tells you to do. And hopefully I'll see you next time.